Okay, so 5.4, graphing and modeling transformations of the sine and cosine functions. So let's recall, given the functions y equals a sine cx, and actually we're going to change that to k, y equals a cos kx, we have an amplitude, and amplitude always has to be positive. Positive. So we're taking the absolute value of whatever that a value is, okay? Because remember, the negative sign on the a value indicates whether we're going to reflect in the x-axis or not, but the actual a value, like inside the absolute value of a, that's going to indicate whether we have a vertical stretch or compression. Okay, period is going to be 360 over k. Okay, and then the critical interval. What a critical interval is like, for example, in the original sine and cos curves, we have 360 degrees. Okay, when we divide it by 4, because we know we have 4 sections in the sine and cos curve, what happens is we get the critical interval of 90. That means every 90 degrees, we're plotting a point. Okay, so I'll explain this right here. Okay, so number 1, amplitude. The amplitude of a trig function is defined as half the distance between the max and the min values. Okay, so for example, the distance between the max value of 1 and the min value of -1, well, the actual distance is 2, so half of that is 1. The normal sine x curve has an amplitude of 1. Okay, cos curve as well. The actual distance between 1 and -1 is 2 units. And it's half of that, so we divide it by 2. And again, the y equals cos x has an amplitude of 1. Okay, when we talk about critical interval here, we talk about plotting a point. We plot a point 5 times, so there's 5 points, 5 critical points, but there's like 4 sections in the graph, and that's why we divide it, the period, by 4. So if we go here, we can see that's 1 section. That'd be the 2nd section. That'd be the 3rd section, and that would be the 4th section. So a vertical stretch or compression will affect the amplitude of both sine x and cos x, okay? And as we can recall, if we had like a general function f of x, this a value right here is either a vertical stretch or compression. It depends on what that number is. So if that a value, and we talk absolute value, so we're not looking at the positive or negative, just looking at that the actual number portion. If it's greater than 1, then there's a vertical stretch by a factor of a, okay? And then that means that the graph will be taller. And then if it's a fraction of a number, in other words, between 0 and 1, then it's vertically compressed by a factor of a, and then the graph will be shorter. Okay, and then in general, sine x and cos x, when we have this a here, we have an amplitude of a units. This always has to be positive. Okay, so example 1, state the amplitude of each of the following. Okay, y equals cos x, we know that there's an imaginary 1 here, so the amplitude's 1. Okay, y equals 3 sine x, this is the amplitude, amplitude's 3. And y equals negative 0.5 sine x, we take the absolute value of negative 0.5, our amplitude is just that 0.5. It's the positive. Okay, so when we talk about period, the period of a function is the amount of domain required for the function to complete one full cycle, okay, or one wavelength. So for the base sine and cosine functions, the originals go from 0 to 360, and then that would be 0 to 360 again, and that would be one period. Okay, so sine x has the period of 360, At 360, it's going to repeat itself. Cos x also has the period of 360. And again, at 360, cos x is going to start to repeat itself. Okay, so when we take a look at these x coordinates, we're talking about horizontal stretches or compressions. And these will affect the period of both sine and cos functions. So let's recall what we've done before. Okay, y equals f k at x. So if we have a number k that's in this position, this is either going to be a horizontal stretch or compression, okay, of the original function. So if k is greater than 1, then it's actually compressed by 1 over k. Remember, this is just the reciprocal. Okay, in other words, one graph is going to be shorter. If it's compressed, it's going to have a period less than 360 degrees. Now, if we have like a fraction of 1, so if k is between 0 and 1, then it's actually horizontally stretched by a factor of 1 over k. Again, the reciprocal here. So one cycle of the graph will be longer than 360 degrees. Okay, and in general, the graph sine kx or cos kx, both of these will have a period of 360 over k. So period equals 360 over k. Remember the k value directly, what we see in the equation. So determine the period of each of the following. Okay, so this x technically has a 1 in front of it. So the period equals 360 over 1. So the period of the original, as we can see, is 360. Okay, this time our k value is 2. Period equals 360 over 2. So our period is going to be 180. Okay, and this time, this is actually right here. This is the amplitude. So this actually has a k value of 1. So 360 over 1. Okay, so let's not get these two confused. So the period of this one is 360. This one's just going to be vertically shorter. Nothing's happening. So this is a vertical compression. Nothing's happening with the horizontal. Okay, critical interval. To find the critical interval or critical points for any trig function, i.e. the max, the min, and the zeros being equation of axis, okay, what we do is we divide the period by 4. Okay, so we take the period, we divide it by 4, and the critical point occurs every period over 4 units. Okay, so in example 3, we want to determine the critical interval for each of the following. So in this case, we would, if you want to see this like the long way, well, we could say, what's the period? Well, the k value is 1, so 360 divided by 1 is just 360. Now, for the critical interval, we take 360, which is the period, and we divide it by 4. So in the original sine x function, we're going to plot a point every 90 degrees. Okay, for the next one, y equals sine 2x. So what's the period? 360 over 2. So that equals 180. So in this case, the period is 180. One full rotation of the sine curve is going to take 180 degrees. That means for the critical interval, it's going to occur every 45 degrees. So in other words, 45 here, plus 45 is 90 here, plus another 45. Okay, 135. That's what's going to happen. Okay, and C, we kind of talked about this before because this is an extension on the last one. Y equals 1/3 cos x. This is actually the amplitude. So this is going to be the original, okay, which is a period of 360 degrees. So just like the first one, the critical interval would be 360 divided by 4. So to actually extend onto this, what if we had, and I'm just going to add a d here, what if we had cos of 1/4 x? Okay, how would we do that? Well, again, the period is 360 divided by the k value. And the k value is directly what we see in the equation. Well, 360 over 1/4, we can't really do that. So what we're doing is 360 divided by 1/4, which is 360 multiplied by the reciprocal. Okay, and I believe we get 1440. In this case, 1440 is very, very long, right? And this is a cos function, so it's going to look like this. Super long. It's going to start at a maximum, go to a min, and go back to a max. One full rotation is going to be that 1440. Well, for our critical interval, if we take the 1440 and we divide it by 4, what do we get? Okay, we get 360. So a critical interval is going to occur every 360 degrees. So that would bring us 0, 360, 720, and then 1080. Had to calculate that. So phase shift. The phase shift of a function is the number of units that the function is shifted to the left or right. So in the originals, because it's the parent function, there is a phase shift of 0. Okay, we consider this as sine x, this is cos x, to be the parent function. Now, a horizontal translation or a shift, okay, these words are the same, or mean the same, will affect the phase shift of both sine and cos functions. So just as a recall, and I think we may be calling this d or h, that's fine, y equals f, x minus h is a horizontal shift of the graph f at x. If h is greater than 0, then it's shifted to the right h units. However, this looks negative. And if h is less than 0, then it's translated left h units, but this one looks positive. Remember that there's that built-in negative sign, okay? So built-in negative sign, so everything looks opposite. Okay, so in general, when we have functions that look like this, y equals sine, and then if there's a number in the bracket with the x that's added or subtracted, or the cos function, that's going to be a shift left or right. Okay, so example 4, determine the phase shifts of each of the following. Okay, A, that's the original, y equals sine x, no phase shift. Okay, y equals sine x plus 45. So because it looks positive, this is actually going to go to the left 45 degrees. Okay, and y equals cos x minus 60. Because this looks like a minus, it's actually going to the right 60 degrees. Okay, and like we've seen before, it's necessary to factor out the coefficient of the term in the bracket in order to identify what the phase shift really is. So if we look at this, we can say the k value is 2. That's not going to change if we factor it out. What's actually going to change, and I'll not underline that, okay, we have to factor out the entire coefficient of x. So we would get y equals sine 2 bracket, and that's what we want. We always want it in this form where there's a bracket and an x right inside the bracket. Okay, minus 90. So in an equation, you're still going to be able to identify, oh, that's a horizontal compression by a factor of 1/2. However, what you're going to get mixed up on if you don't factor it is that this is actually going to the right 90. instead of going to the right 180. Okay, very different. Okay, and let's factor out this coefficient. So this was a little bit trickier. We have to factor out the entire coefficient of x. So we're going to factor out negative 1/3. Okay, quite an ugly number. So we have y equals sine. We're going to have negative 1/3 bracket x. That one's easy because those are the same number. Now, if you have trouble with this one, take it to the side of your paper. We're doing 60 divided by 1/3. Guys, this negative and this negative cancel, so it's actually going to be positive. Okay, well, what's 60 divided by 1/3? We actually have to put it beside each other. And we know we can't divide fractions, so let's multiply by the reciprocal. 60 times 3, I get 180. Okay, so this originally looked like it was going to the right 60, but it's actually going to the left 180. Very much different than the original. Okay, and this would be a reflection on the y-axis, and this is a horizontal stretch by a factor of 3, just to identify those. The equation of axis. The equation of axis of a trigonometric function is a horizontal line in the form y equals y-intercept. Okay, this is just that form that we use because it's not in the form y equals mx plus b. Okay, and it's drawn through the center of the graph. So, with no transformations on these functions, sine x and cos x have the equation of axis of y equals 0, both of them, okay? So a vertical shift or translation will affect the equation of axis of both the sine and cosine functions. So if we can recall, and we're going to change this to a c, okay? If we can recall, y equals f at x plus c is a vertical translation or shift of the function. So if c is greater than 0, then it's vertically translated c units up. And if c is less than 0, then it's vertically translated c units down. Okay, so in general, y equals sine x plus c and y equals cos x plus c have an equation of axis of c. Okay, so in number 5, determine the equation of axis for each of the following. Okay, so in the original, we're looking for the c value. So it's actually plus 0. So y equals 0 is going to be the equation of axis. Okay, the EOA, equation of axis. Oh, that's OA. I always put AO. Okay, of this one, it's just going to be 1/2. So it's y equals 1/2. Okay, and the last one, y equals cos x minus 2. Our equation of axis is going to be y equals negative 2, right? Because that's down 2. This one's up at 1/2, and this one has no vertical translation. So here's your algorithm for curve sketching. And the word algorithm, if you're thinking, what does that even mean? It's basically just like your steps, okay? The steps that you go through to curve sketch, okay? So we complete the sketching in 2 steps, okay, if we're not using mapping notation. So what we do first is we complete stretches and compressions and reflections. So if you remember like the bed mass, this is everything that you have to multiply or divide. Okay, so what we do first is like we label our x-axis using critical intervals. Okay, I want to note this though, if there's going to be a phase shift, and like generally what I personally stick to is like 30, 60s. If there's a phase shift of 30 and 60, use 30 as your scale, even if the critical interval is bigger, because eventually you're going to have to come back to this 30 and shift your graph. Okay, and if there exists a phase shift of 45, we're going to use 45 as our scale. Then we're going to label the scale on the y-axis with the amplitude. Okay, so we're going to label it A units up and A units down. Okay, so say the amplitude was 5, we go up to positive 5, down to negative 5. So pretty much we're labeling x-axis with critical interval, and then the y-axis with our amplitude. Here's the short form, okay? And then what we're going to do from there is we're just going to plot our critical points, and I did this straight patterning. Okay, so I'll tell you what these mean. Sine x. So usually what sine x does is we go, and it says right here, equation of axis, max, equation of axis, min, equation of axis. And then we connect. If we had a reflection, we would say equation of axis, min, equation of axis, max, equation of axis. Okay, and we already talked about how every x-intercept just stays there. Okay, that's what those two mean. Now, these two, cos x, what usually happens in cos x is we start maximum, equation of axis, minimum, equation of axis, maximum. Okay, that's our original. But if we go and we reflect it, we're going min, equation of axis, max, equation of axis, min. Okay, so keep this handy. After you're done graphing, so steps 1 and 2 are all the stretches and compressions. After we graph that as the first step, we can go ahead and just shift it. So we just shift it left, right, up, down. Okay, left, right using our phase shift, up, down using our equation of axis.